So far we have talked about random sampling, but there are situations where we might need to do systematic sampling. And how systematic sampling work is that suppose you have 10 units or 20 units, n units, which is just 20 units, and then you select a random integer, say k, and say k is 5, so n over k here is 4, so all the units you're gonna get, all the samples you're gonna get would be of size 4. So you have 1 2 3 4 5, and you then in that you randomly select one, and then you select every kth unit. So this is 5 13 18 and so on. So so this is also called as a linear systematic sampling. As we can think of units arranged in a line. Now here is when you selected k, which was 5, this was an integer. So how does that work? So we think when n by k is an integer, n by k is, and this is the sample size, you pick 1, and the next item you're going to pick will be 1 plus k. So this is the second item. The third item you will pick will be 1 plus 2k. So it's a third item, but there is 2 here. So the last item is going to be 1 plus n minus 1k. Okay, so we can thus think of the whole population being grouped into k disjoint groups. So this is, if we had selected 1, then this is this group. If we had selected 2, then this is this group. If we had selected I, this is this group. If we had selected the kth number, then this is this group. So basically what it is a simple random sampling of one such group from k possible groups. So this is a simple random sampling of one single such group from k possible groups. And this is important because what happens here is n becomes 1 when we consider this into a simple random sampling, and this thing will come up later. So when n upon k is not an integer, then the sum of the possible samples will vary by 1 unit. So when we had 20 and we selected the k to be 5, the n becomes 4, so all units will become same. But what if we had selected k to be 6? Now you have the first 6 units, 1 2 3 4 5 6, and say you selected number 1, then it will be 1 plus 6, that's going to be 7, 7 plus 6 is going to be 13, 13 plus 6 is going to be 19. So you are getting 4, but if we had selected 6, that would be 6 plus 6 is going to 12, and 12 plus 6 is going to be 18, and so you only have 3. So you are getting different sample size, which is not ideal. So what we then consider is called a circular systematic sampling. So imagine them that all these units are in a circle with n. We take the k as the nearest integer, so 20 over 6 is 3. We'll take 3, it will take as an integer. Now we take any random number out of n, 1 of I n, and then take this number, and then take every kth unit, then we will take every kth unit, like every third unit, till we get, and then you might cross this and finish it. So for example, we have n units. So to want to take the k is going to be nearest integer to n by small n, which is the sample size you want to take. Then take any random number between 1 to n and take every kth unit after that in a circle till n units are selected. N is 30 and we want to take n is equal to 8, then k is going to be 30 over 8, which is supposed to be 4. Now we'll select a random number out of 30, say 14, and then keep picking 14 plus 4, 18, 18 plus 4, 22 till 8 units are selected. So here's a question. If n is equal to nk, because k is basically n divided by n, so n is equal to nk, how many distinct systematic samples can there be? So obviously we have seen this here, that the distinct systematic sampling can be a. But what is the probability of selection of each? So they are going to be k samples and each will have a probability of 1 by k. And to think of that is, say n is 100 and we have a n is equal to 20. So then it will be 100 is equal to 20 times k, or k is equal to 5. Thus, how many samples we can have? We can really have only 5 samples, right? We have the n is 20, so 20, 20, 20, 20, 20. That will comprise of 100. So we have 20, 20, 20, 20, 20. We have 5 samples. Now the first thing that you do is you select one number for any sample, right? You select a number to do the systematic sampling. The way you would do it, you will select all these in 100 and then you select first 5 and you select one number out of it, say 3, and then you keep adding it to get the whole 20. So what is the probability of this number getting selected? 1, 2, 3, 4, 5. The probability of this number getting selected is going to be 1 over k. So the probability of, and once you select a number, the whole sample is pretty much decided. So the probability of that sample being selected is just going to be 1 by k. For a systematic sample of size n, let sample observations. So you selected a sample of size n and then you selected their y values for each. So you have 1, 2, 3, 4, 5, 6, 7, which is your n, and each of them have y values. So these are y1, y2, y3, all the way to yn. And the sample mean is, instead of just saying y bar, it is called y bar st. This is the systematic. So how will y bar st be? Y bar st will just be 1 by n, I is equal to 1 all the way to n yi. This is the yst. Now if we can prove that if n is equal to nk, then y bar st is unbiased estimator of population mean capital Y bar. Now there is another thing to consider about systematic sampling. The variance among within same sample. So what does that mean? What that means is that if n is equal to nk, all samples will be of size n. Let y I j denote the population value of y from jth members of ith systematic, right? So there are I systematic I groups, and each of these members are j. I represent the groups and j represent each member of it. So the within sample variance, this is called WSY, which is the within sample variance. What would that be? This is going to be k n minus 1. Now we're going to do summation here, two summations. I is equal to 1 all the way to k, because there are k samples, and j is equal to 1 up to n, because each of them is going to be n members in each sample. And we are going to do y ij minus y bar. This is y bar I. So what we are doing is, for each sample we are doing this y ij minus y bar I, and then we are adding it up for each groups. So if there is this group, this group, this group, and this group, and each of them has 1 2 3 4 1 2 3 4, we're gonna get a y bar 1, y bar 2, y bar 3, y bar 4, and then we're gonna subtract, and these are represented by yij's. So this, for example, this would be 1 of I, and then there would be 2 of I, and then there would be 3 of I, and then we're going to subtract 1 of I from yi1. And then we're going to add them all up for each of them. So what we are basically, and then we're squaring it. So what we are basically, so we are doing this for this, for this, for this, and we, so what we are actually only considering is within sample variance. So what it means is that if the units are heterogeneous, then S square WSY will be high, otherwise it would be small. Now, so that is the S square WSY, but then there is variance of y bar sy, systematic sample, that is given by S square 1 minus 1 upon n minus k n minus 1 S square WSY, and then you can, so that's the variance of y square, or variance of y bar in systematic sampling. And then you can substitute this thing here. What you will get is S square 1 minus 1 upon n minus 1 upon n yij minus y bar I square. So the variance of the estimator does not depend on the sample size, right? There is no sample size in there, and there's no n here. And a larger sample will not lead to a more precise estimator. So the variance and this is y bar st, and it is not so that's the variance. But when we think, let's now think about variance of what is the variance of y bar in systematic random sampling in SRSW-OR. That is S square over n, 1 minus n over n. So what we can see from these things, these two, because this is the same here, that variance of y bar systematic is less than the variance of y bar if and only if the S square is more than S square. They cannot be directly compared because this one is S square 1 minus n minus 1 upon n summation this, while this one is S square upon n and n upon n. But what we can stipulate from this is the variance of y bar st is going to be less than the variance of y bar if the within sample variance is more than the population variance. So systematic sampling is more precise than if within is more than overall variance, and it is less precise otherwise. Systematic sampling will be imprecise when the units within the same samples are homogeneous. And we can intuitively also think of it, because if we are taking a bunch of samples and a unit and a population has some degree of variance, but we are selecting very homogeneous systematic samples, so each of their variance is not going to represent the variance of the whole population because they are so homogeneous. So only when this within it is capturing more variance than what can be captured by S square, then we can say that the variance of y bar st is less than the variance of y bar, or we can say that this is much more precise than this, only when S square is more than the capital S square. So another form of variance of the sample mean. Now we can also consider this as a rho correlation, which is correlation rho W. It is rho W denotes correlation coefficient between pair of units that are in the same systematic sample. So variance of y bar st is s square by n, 1 minus 1 upon n, and 1 plus n minus 1 rho w. So if there is a positive correlation between, then the variance of the estimator increases. So if there is positive correlation variance of y bar by systematic random sampling is s square by n, 1 minus n upon n. So variance of y bar st is less than variance of y bar if one minus 1 upon n, 1 plus n minus 1 rho w is less than 1 minus n upon n. Now if n is very large, then we can ignore this whole thing, this and this thing can be ignored, and then what it will become is 1 plus n minus 1 rho w is less than 1. So what that means is if rho w is less than 0, then only it will hold true, because if rho w is more than 1, then this whole thing is going to be more than this will not be, this whole equation will not be true. So rho w has to be less than 1, it has to be a negative number. So systematic random sampling is more precise. So a systematic sampling is more precise than if and only if rho w is less than 0. In fact, because of this multiplier here, 1 minus 1, even a small positive correlation will lead to a wide increase in this, because it's multiplier. Say if this is rho is only 0.2, but this n minus 1 is 20, then it will become 4. So even small positive correlation will lead to wide variation, and so the values are not supposed to correlate with each other. Now, what is the advantage of why should we do a systematic sampling? Well, there are some simple examples. They are easy to draw, easy to implement. For example, you don't even have a sampling frame. Even then, you can do a systematic sample and can be done, and it's also easier to implement. Because so for example, you're doing a sampling, you just select one random number, and then you keep going every kth number. And also it is also very good when we believe that there is a trend in the population value, then the effect of the trend is removed more effectively by systematic sample rather than a simple random sample. The next thing is estimation of variance of sample mean. Estimation variance of So in SRS WOR, variance of y bar was small s square upon n, 1 minus n upon n. And this was a, and you can do it, the whole variance of the y bar, you can calculate or predict it based on, estimate it based on the sample variance. In systematic sample, we cannot get, in systematic sampling, we cannot get unbiased estimate of the variance of sample mean. The only time we can actually do it is if we have to assume that the ordering unit units is completely arbitrary. Then, and only in that situation, then variance v hat of y bar st is equal to variance of y bar st, or sy, st I think is the word, which is equal to small square n 1 minus n upon n. And this is the same as the SRS WOR, and it will be unbiased, assuming this model is true. But we can never be absolutely sure that the model assumptions hold at all times. And why is this? Because if you look at this variance of y bar, it is s square over n, 1 minus n over n. The problem is the s square here is 1 upon n minus 1, or this is the small s square, is yi minus y bar square, right? But when we are doing a, this is small s, because we have the predictor here, that the small s square, that here in systematic sampling, the n, we had talked way back earlier here, that n is actually 1. So if n is 1, then we can't really do this, because this will become 1 minus 1 or 0, or s square is going to become 0. This is actually going to become 1 by 0, which will be not a computable number. So that's why we can't compute it, and that is why this does not work for systematic sampling.